First, I'd like to thank the organizers of this conference and to the reviewers for their comments on our submitted abstract. I will present work in collaboration with Tania Palacios and Sandra Smith, and the purpose of the talk is to share results on collective foraging in spider monkeys, placing a particular emphasis on the implications of these results for collective intelligence, discussing the relevance of studying natural systems when learning how intelligence can be distributed and how systems can be designed and controlled based on those principles. Many of humanity's achievements are products of collective intelligence. In many cases, systems are designed so the information transfer and the decision-making involved take advantage of the fact that no individual mind has a complete overview or the capacity to make a decision about a collective problem. This photograph is from the control room of the government of Chile's CyberSyn project. This was a system designed specifically to collect, analyze, and make decisions in real time on the management of the public companies, mainly those in charge of energy. The very disposition of the control room, as well as the software that integrated and displayed information, spoke about the distributed nature of the information processing and decision-making that was supposed to take place. Our study system is fission-fusion dynamics. This is a grouping pattern that can be observed to different extents in different species. It consists in the subdivision of a larger unit, the group, into smaller units or subgroups, which constantly change in size and composition. In the animation in the middle, you can see a group of triangles, all belonging to the same larger unit, but coming together and splitting continuously. This grouping dynamics was first described in Hamadryas baboons in the 60s, and later found in other primate species, such as spider monkeys, the species that we study, and chimpanzees. After that, it has been described in many other species, mainly of mammals, including hyenas, dolphins, elephants, and even some bat species. Based on evidence from contemporary hunter-gatherer societies, anthropologists believe that our hominid ancestors also lived in groups with fission-fusion dynamics. And what all the species have in common is that they feed on resources that can be found in patches, which vary in distribution and abundance, both in time and space. In the case of frugivorous animals, fruit is found in trees of different species, each with a variable distribution and timing of fruiting. This is 1 year of fruit availability in a section of the spider monkey's habitat. Important trees in the diet of spider monkeys are shown in gray, while only those with fruit during a particular month are colored in green, with the intensity depending on their fruit content. So this is a highly dynamic environment, with months of relatively high abundance of food and others when only a few trees have fruit available. This temporal scale, monthly, is closer to what spider monkeys have to deal with. Many trees have fruit for about that time. So the question is, how do they find resources in such a variable environment? One consequence of fission-fusion dynamics is that foraging for resources can be done in flexible sized subgroups. The size of these subgroups matches, to some extent, both the local and global abundance of resources. Both at the fruit tree and the habitat wild scale, larger subgroups are found when there is more food available. So in the graph above, you can see the relationship between the size of fruiting trees and the average size of a feeding subgroup of spider monkeys. In the graph below, you can see how subgroup size changes as the overall fruit abundance in the habitat increases. When there is a wide variation in the food abundance, there is indeed an increase in subgroup size. As food abundance increases, that's the red line. In other situations, when food does not vary so much, the opposite relationship can be found, that is the blue line. So subgroups seem to be matching the food availability in the environment. And the question is, how do they do this? So we have foraging in subgroups that spread over large areas, and these subgroups are constantly splitting and coming together. So we wonder if by spreading and coming together frequently, they could be sharing information about feeding sites. and if so, whether we could consider this an example of group cognition or group intelligence. So we have carried out observations that have allowed us to detect which individuals know about a fruiting tree. By noting when these knowledgeable individuals are followed by others that have not yet visited that tree, thus being naive about the presence of fruit there, we can construct networks of followership that effectively represent the flow of information about fruiting trees. So here the network shows the different individuals in the group belonging to different age-sex classes. And the directed links between them show the frequency with which a naive individual followed a knowledgeable one. There are some individuals that are followed more by others, but most individuals are followed at least infrequently. And this creates a cohesive network where information about fruiting trees reaches the whole group. We have also studied the way in which individuals are attracted or repelled from one another. Given that fission-fusion dynamics implies that individuals have the option to leave or join a subgroup depending on who is already there, we can study these decisions directly from continuous observations of subgroup composition. In this network, the nodes are individuals of different sex, denoted by shape, while the directed, weighted links correspond to significant effect of the absence of an individual in a subgroup on the presence of another one. Gray links correspond to attractive effects, that is, the absence of an individual is followed by the absence of the other, more often than expected by chance. And red links to repulsive effects, that is, the absence is followed by the presence of another individual, more often than expected by chance. So as you can see, there are many more repulsion than attractive links. When we run a community detection algorithm on the network of attraction, several clearly clustered communities appeared, represented here by the color of nodes. The attractive links occur mostly within these communities, while the repulsive links occur between individuals across and within communities. This fact that the repulsion network is more diffuse could have the consequence of spreading individuals widely apart, thus gaining more information about the location of currently available resources. With those networks, we simulated new data sets of subgroups that resulted from those same attractive and repulsive interactions, assuming different levels of relevance of those influences based on a threshold parameter. For some values of the threshold, we recover the original frequency distribution of subgroup size, which suggests that a potential way in which subgroup size can be adjusted to a dynamic environment is precisely through the individual decisions on whether to leave or join a subgroup, depending on the presence of others. In other words, through these micro-level decisions, the group as a whole achieves a global solution, that is the subgroup frequency distribution, which matches the resource abundance. So, wrapping this up, if we define intelligence as solving a specific problem by processing information, in the case we're dealing with here, the problem would be how to find resources in a patchy and dynamic environment. And the solution we propose, that spider monkeys are arriving at, is to pool information gathered by distributed foraging. The next step is to test whether this pooling of information is convenient, in the sense of being synergistic. That is, when the partial individual estimations of the whole or true distribution of resources are minimally correlated and complementary in their estimation of the target distribution. So, for example, we could study individual home ranges, Y1, Y2, and Y3, and an estimated distribution of abundance of fruiting trees underlying this area. The union of all individual home ranges would constitute the target distribution, X. And the task would be to evaluate whether the overlap of individual home ranges is synergistic, that is, minimally correlated and complementary in the estimation of the target distribution. Postulating collective intelligence in this form would fall under an extended mind argument, that is, that minds go beyond the individual, including many tools that could be considered as part of the mind. Finally, I would like to acknowledge the support of different institutions and people, and thank you very much. I look forward to your questions.